Most safety-critical systems have some software that is highly safety or mission-critical, but other software that is less critical. There are two main signs that you have a problem with low-integrity tasks being able to compromise the safety of your high-integrity tasks. First, if the low safety integrity or SIL software can access critical task data without going through a high SIL gatekeeper first, then the low SIL software can corrupt the high SIL software's operation. The second sign is if the low SIL software can affect the timing of or even block critical high SIL tasks from execution. It is critical to have isolation between different safety integrity levels in a safety-critical system. We'll consider the general case in which you have some lower integrity non-critical tasks, but also some higher integrity mission or safety-critical tasks running in the same system, and make sure that the low SIL task cannot interfere with the high SIL task. In general, the lower SIL software is assumed to be able to compromise the operation of the high SIL software unless you can demonstrate isolation. For the purposes of isolation, the higher SIL software is presumed to be perfect for practical purposes, or you can think of it as trusted. What this means is that we're going to assume the high SIL software was done correctly, because it was developed using high-quality development processes and validation. That's not to say it's perfect in a mathematical proof sense, but rather we're going to assume that the higher SIL software does not have any defects that matter, and use isolation to make sure that a concurrently running low SIL software doesn't degrade the performance of the higher SIL software. The lower SIL software might just be ordinary everyday software, or it might be safety-critical software developed to a lower SIL. But for isolation purposes, it's basically untrusted. That's because less engineering rigor was used to ensure that the low SIL software is actually correct, and that includes less rigor used to check whether there are bugs in the low SIL software that could corrupt other software in the system. Those bugs could take the form of corrupting data values, affecting timing, changing hardware configuration, or other interference. Because the lower SIL software could crash or corrupt the system operation, you need isolation. Your best bet is to use hardware isolation in the form of completely separate microcontroller chips, with one chip for each SIL in the system. If the safety functions implemented on a chip share that chip with non-safety functions, then all the software on that chip must be developed to the highest SIL of any function on that chip, unless you can prove on-chip isolation, which typically you cannot. So, for example, you might find a critical microcontroller chip that has SIL 3 and SIL 4 functions allocated to it, but with all the software written to SIL 4 because that's the highest SIL on that chip. There might also be a low SIL microcontroller with SIL 1 and SIL 2 functions allocated to it, but with all its software rounded up to a SIL 2 implementation. The need for isolation goes beyond just the microcontrollers and includes the networks. In this example system, there would be a need for both a critical network and a separate isolated non-critical network to avoid the non-critical system interfering with critical network messages. Any communication between the networks would have to be handled by a firewall designed to the higher integrity level to make sure that no spurious data made it on to the critical network.